Homerding from Argonne National Lab. I want to talk to you about some performance analysis I've been doing on the US Department of Energy proxy applications and subsequently our Optimism Annotation exploration tool. So to provide some context for the talk, I'll give a brief overview of what proxy applications are, what we use them for, the HPC performance analysis that we do, and how we tie that into doing compiler comparison to study how well Clang is performing compared to ICC and GCC. From there, some of our findings led us to look into how we model map function memory access. So we're going to talk about how we go into that. It leaves a few open questions that we're going to try to answer with the Optimism Annotation tool. Very quickly, the ECP Proxy Application project is part of the Exascale Computing project in the US. It's co-designed between a bunch of national laboratories and vendors. So proxy applications are small, somewhat easy to use representative kernels and smaller portions of scientific code bases that we can use for co-design. They're also useful for studying with compilers because they present a fairly complicated code, but they're not full production code level bases that pull in a lot of side things that make it difficult to build and run and test. If you're interested in running with some of these, there's a website that contains a suite with 15 that are hand curated and then an additional catalog that contains about 55 proxy applications. You can just Google ECP Proxy Apps to find it. As I mentioned, it's a nice balance between complexity and usability. Some of the limitations are that they're designed to be played with, so they're not really set up to just build and run like a regular benchmark. So we're kind of working on that right now, but generally you have to set these up to run yourself. Okay. Going into the performance analysis work that I do, we're trying to study exascale computing and how these problems scale up. Which is important for me, but not particularly for this area. But we boil down to when we look at different compilers that we use for this. So we just get a good build with each compiler. We identify when there's room for improvement, particularly in Clang, because I work on LLVM. And we are able to specify this as I collect a lot of performance counters, and we're able to tie these into our source code lines, and from there we can see if we're pressuring the actual hardware limitations or are we just not getting the fully optimized code. Some basic results here. These are all normalized against GCC. Sometimes Clang is significantly better, sometimes we're worse. Essentially when we find that we're worse, we're going to look into it. So one example for RSBench, which is on the end, which we're performing slightly worse than GCC and quite a bit worse than ICC. As you can see here, this inner loop, which contains a call to ghost and sign with the same argument. Now this, when you build, is two calls for us. GCC combines these into sign ghosts. This is built without fast math because we need the accuracy. So we want to combine these calls, but we want to also make sure that everything around it is fully fleshed out. So looking into the design here, we want to handle our special case, which is combining sign and cosine, which we can do just because we know that they both can touch memory in the exact same way, writing Erno. But we also want to just model the Erno access across all the limma functions where it matters. So we do this by using the write-only attribute. So coming out of CodeGen, we're going to mark these functions as write-only, as they can only write to Erno, but that doesn't really do enough to make sure that we get all the support that we want, so we go into the back end and make a few improvements, improving early CSE, trying to use the write-only attribute, but then also we want to infer it on additional functions so that we have better coverage since we're improving the usability. Another important aspect that we want to look into that's going to come up again later is exposing this stuff to the developer, is having an outside way to mark these things, mapping essentially the LLVM attributes out to source code. A lot of them are, some of them are not. So we're creating a write-only attribute in Clang. So looking at all of this, we have a lot of open questions that kind of came out of this. So it turns out that we just didn't have the information and we weren't using the information properly. So from a performance engineering perspective, we want to be able to understand kind of what information could we encode that we know but the compiler cannot infer. Does that performance actually improve, or does that information actually improve the performance? And if it doesn't, is that because the information was not useful, or is it because the information was just not used? Then after that, we want to know kind of what information should we add to get that performance, not just what can we add. And basically, what is the performance gap that we're working with here? How much bang are we going to get for all this effort? So as another example of kind of motivating this, we're going to look at this code segment here. So here we have an external function, a global pointer. We're going to call the function, and then we're going to basically collect into sum. Now, if we want to get a fully optimized version of this, we want to encode the information that we know as a developer, we could add the attribute pure to the external function and the built-in assume to make sure that we know we're not going the other way on the lower and upper bounds. Now, just jumping from here to there is fairly easy, and then you can get a fully closed form expression, which is a good optimization for us. But actually, how we got there without just changing the slide is fairly difficult. So these things are not always obvious, especially if you're coming from a developer standpoint, not from the compiler, because a lot of times the compiler is viewed as something of a black box. So we're trying to build a tool that kind of gives us some insight into what the compiler is doing, and also give us some suggestions out trying to tell us what kind of things we could do that would actually influence the code. So this is let into our tool, which does optimistic annotation. Essentially, this means that we're going into LLVM, finding all the locations where we could have additional information, and then trying to find the most optimistic information we could add there and adding it without breaking the code. Now, it's important to mention here that breaking the code just matters on a verification test suite. So obviously, we're not proven correct, but we're leaving that as a step for the developer. We're trying to isolate information that we could add that will improve performance that the developer can then go and decide if it's correct or not. So essentially, we're just trying to take the large search space of all the types of things you can encode and shrink it down and make it very manageable for the developer to try and get some additional performance and use a lot of the functionality that's in the compiler that's just being limited by some special cases that will never actually happen. So talking about how this works, as I mentioned, we have a verification that we depend on for the developer to present, which decides whether or not the code was compiled correctly, but it's not testing all code paths, so this is where we're kind of being optimistic about it. So we compile, we check against the verification, it comes out successful, as you would hope so for the regular start. From there, we start adding annotations. So we identify all the places that we will be able to add, and then we try to add in information, like marking this parameter as read none. So we, once again, compile and we verify, and this time we fail. So we're going to step forward. We're going to go with something a little less optimistic. Instead of read none, let's try read only. And this time we get success, so we're going to leave it in there. Now, this doesn't prove that this parameter is read only, but we leave that to the developer once we kind of figure out which of this information is important for performance. I'll talk about how we kind of go about adding this information. So we identify all the locations, which in our benchmarks, we went anywhere from around 100 to 1,000. We list these out in a list, and each identifies a particular opportunity, and then the value within there will identify how optimistic of a choice we made. So there's anywhere from no alias, which will just be a value of 1 or 0, depending on whether or not no alias compiles and verifies. We can add read none, read only, write only as reducing things, and then the function memory attributes, we end up having 13 different choices. So to try and cut down this search and not run forever, we start by filling everything in the most optimistic, and then we start cutting in half, doing a binary search through this. As you can see, so we run with all this, that verifies, we lock those in, and then we continue on to the second half. When we hit a point where something does not verify, we work and we try to reduce the values. So this started at 13, we drop it to 12, we drop it to 11, we keep going until we get verification. So we go through all of these steps, which can take a while depending on the amount of code that you're looking at, and get a final control string list of optimistic choices that we made that compile and verify. Just an example for the types of things that we're writing for function side effects. So our most optimistic choice, spectable and read none, and then just read none, read only, and on down the line. So these are more or less ordered by hand. There's usually not as many. This is the largest list we have. So we basically are working through a long search space of places we can add information, and then a smaller search space of what information we can add in those places. The type of things we're identifying as locations to add information, aliasing pointers, parallel loops, unknown runtime exceptions and functions, function side effects, pointer usage, as you can see, everything listed here. So once again, this is a very large search space, and I know some of the developers at HPC that has tried to do some of this by themselves. They'll spend days just adding in annotations and then figure out if it even does anything and then figure out if it actually helped. So we're very much trying to shrink that work and automate it as much as possible. So I want to show some results from this. These are, once again, some of the proxy applications and their run configurations, which are important for these because they need to be run in a way that's representative of the actual application that they're representing. So here, what you can see, the successful compilations refers to the number of times that we added information and compiled and verified successfully. Out of that, there's a subset which we're calling new versions, which are the times that we compiled and verified successfully after adding information, but it changed the executable from a bit comparison. As you can see, it's somewhere between 10 and 35% of the time we're getting a new version out of these. So this does result in quite a few new versions, but not that this information is constantly making a difference in the compiler. And then the last column, optimistic opportunities taken. This refers to our total list of places that we can add information and how many times we were able to add some optimistic choices that did not break the build. So to really quickly kind of touch on some of the strengths and weaknesses of this tool, the big weakness, we can't prove the correctness for this, but that is the idea, is trying to assist the developer in identifying locations where he can provide information that they know that we cannot analyze in the compiler completely. But the benefit here is that we can target this. We just decide which code we want to look at. We don't have to discover the whole code base, especially for HPC. A lot of the times there's performance critical parts and a lot of extra code, so we're able to focus it in, and that helps to limit our runtime and number of compilations and search space that we need to go over to be able to present these choices to the developer. So going into it, I'm going to present a few of these graphs for these proxy applications to go over kind of what you're looking at here. The dark line that's steadily climbing is just representing the overall tuning time that we take to figure out the fully optimistic choices that we can make. Along that lines, you see little red dots, circles. They are representative of the times we compiled, and we added information, and we verified, but nothing changed from the previous one. Contrary to that, we have the blue line, which represents our speed up relative to the baseline, which here the baseline is the just regularly compiled code with no additional information added in. And then you see the small black diamonds on there. Those represent our actual new versions where we added information, compiled, verified, and it did actually change the resulting binary. And then we see our speed up that we like. So for RSBench, which is a compute-bound kernel running with OpenMP on 72 threads, we see a very quick jump after adding information twice to about a 10-12% speed up. Then we continue on, we get a little more of a speed up, and then another nice jump, and we end up seeing around a 20% speed up. So this kind of defines that question of how much performance are we losing by missing information, with the caveat that this is not proven correct, it's just working correctly. So it depends on the strength of your test suite a lot. So this is about what we would be expecting as more information can help the compiler to perform more optimizations and we get some better run times. Moving on to the next one, we see something a little stranger. So we add some information, we get a nice speed up, we add a little more information and we lose it again, which is understandable when you think about it, but is interesting. So Pathfinder, another one. This time, you'll notice compared to the last two, where our tuning time is in the order of 400 seconds, this time we jump up to about 4,000 seconds. This is our application that we looked at that ends up producing the most versions, but it only has about the same amount of optimistic choices to make as the previous two. Part of this is the fact that the application itself just has a longer runtime. So throughout this, for verification, we have to run and check the output against, so that can very much increase your runtime. But like I said, you can focus this down to specialized areas if you need to cut that down. But it's fully automated, so just run it overnight. As you can see, we kind of steadily climb here until we get a nice speed up, about 17%. This is on molecular dynamics code. Here is the first time we see a slowdown from adding information in. So this led to some future work we're trying to work on. So, well, we'd like to be able to suggest places where we can suggest annotating the code to see a performance after you prove that it's correct. When we see things like this for the compiler, we want to figure out, okay, why is this hurting? So we're working on developing an isolation pass to decide what's happening here, so we can look into the actual code base there and see what kind of things are turning off. So the first three, we're seeing a nice speed up. When we get here, we don't actually end up getting any speed up, and there is one strange case where we slow down almost an order of magnitude. But this is the application where we have the most optimistic opportunities to work with. So there's like something like 700, where the first couple all had around 200 to 300 places to add information. We get a lot of new versions and a lot of versions that add information and compiled correctly, but nothing seems to affect the performance, which ends up not improving anything, but is actually a good information to know for the developer, just knowing that, okay, nothing that we add is actually going to improve this code. The compiler is already handling it everywhere, and a lack of information is not limiting it. And our final application that we looked at, MiniGMG, this is a fairly uniform graph. It produces 4 new versions, none of which have any effect on the performance. We get 16 total compulations that verify. So I wanted to touch real quick, looking at LTO. So a lot of times we don't like to use LTO for the full production applications because it takes a very long time. You have to run it every time you compile. For us, we take a long time to tune, but once we're done with that, you can add in the information after you verify it, and then it's in there. It's set for good. You may need to run it every once in a while, depending on the amount of changes your code is going through, but it's an upfront cost to pay as opposed to having to run things over and over. But looking at the comparison to LTO and thin LTO, we are still seeing a speed up compared, except for in the pennant where we weren't really seeing much of a speed up to start with. So that was kind of the first part of this project, which was to identify kind of our fully optimistic, how much information can we add and what does it do? So that is interesting to us as compiler developers because we're trying to figure out kind of what information actually makes a difference and are we using it. But to make this useful for the developer, we need to be able to point to exactly which places and which information we need to add to make this useful. So we added a second step to this. We're searching back through all of our optimistic choices, and we're isolating the ones that perform performance critical changes. So here we're looking at RSBench, which is our first one that saw a nice speed up. These are the total choices, the long list of everything that we made and the values that we chose for them. So we make a bunch of no alias choices, some read none choices, a little hard to see here, but the basic idea is stepping forward. So we search back through removing this information and then once again verifying, but this time we're running a performance test also, and we're tracking the time to see if it crosses a user-defined threshold. And if it does, then we're gonna say, okay, this is important information, let's mark it, and then we'll present it later. If it doesn't, then we can just say, all right, this information did not help, we're gonna remove it. So after we run this second search through the space, we end up getting 7 locations that it identifies as being important to cause the 19% speed up. So it's very nice to know 7 places you can add information and then you can get a nice speed up once you verify them. And so looking at this compared to the total 250 where 90+% of them were marked optimistically, which you're never gonna go through and verify everything by hand. 7 locations when you know that there is some performance you can gain if these turn out to be correct is a very reasonable thing to do. So from there, we map back to the code base and we try to make a suggestion. So just a couple of examples of what came out of this first benchmark, marking a function as static to internalize it, and additionally adding some function memory attributes to this function that was just in a different module that does not. We actually went through these with the developer and these he was able to prove very quickly. He kind of knows his code and it's found it to be very useful. So I've kind of been touching on it throughout the thing, but our future work involves kind of improving the tool, the suggestions that we work with, also the way we search. We have a lot of options here for isolating and what we define as important. And we also want to run this through a much larger set of tests. The nice thing with running with proxy applications is that they're fairly complicated, so it does represent some of the limitations. We want to also switch the search to identify these places where we see performance regressions so that we can go into the compiler code, figure out which passes were enabled or disabled by that information being present. And then kind of looking at it without isolating things, looking at the full stretch of optimistic opportunities that we can make. We're going to try to run through and collect the LLVM statistics on these to try to figure out, okay, what passes, what information is being used, what information is being added but not being used, to try to take a first step in understanding, is this information useful or is it just not used? All right. To close, I want to acknowledge Exascale Computing Project, which is funding our work. And thank you, everyone. Any questions?
Are you using profiling in any form to actually, reduce your search space? Because it looks like you're looking at the entire code.
No, we are actually using, so as I mentioned in the beginning, I do performance analysis on these proxy applications. So these, as they're already kind of representing a performance critical part of production code, I then am taking a further step to isolate this. So for some of these, we're running over one source file out of about 10. Some of them we're targeting functions. But yes, we are using profile information to work with the total search space.
Okay. The other question was, I mean, it looks like you are looking at a lot of these argument kind of stuff and things like that, but have you looked at things like, let's say you apply unrolling or SIMD or vectorization pragmas and other kind of stuff on your loops?
Depends on whether or not it'll kind of get enabled in the backend. So we're adding this information directly into LLVM. So not directly, as I know.
Okay.
Any more questions? All right. Thank you, Brian.